So this is our fourth lecture on reacting mixtures and combustion. And we've covered how to handle the first law of thermodynamics. Basically, you get an energy balance equation like this. What was the very new term for that energy balance equation? What is the name of this H bar F naught? Enthalpy of formation. It's on a molar basis. Why did you need that? Because of a consistent measure of energy when you're changing the carbon from a hydrocarbon into carbon dioxide and the hydrogen from a hydrocarbon into water. And so you have a consistent measure of energy when you have these enthalpies of formation. Now we need to talk a little bit today. We'll introduce the adiabatic flame temperature. So some things can burn and you have an adiabatic. What does that word adiabatic mean to you? No heat transfer, no work transfer. Well, this is typical, but no heat transfer, that's adiabatic. And what will happen is that the products come out at a very high temperature, and that's called an adiabatic flame temperature. All right. Different gases burn at different temperatures. If you're a welder, you know that. If you've done brazing or soldering, you know that. All right. And so different fuels will be chosen so that they have a higher temperature. Then we'll talk about the second law of thermodynamics. What do you think that equation looks like? Well, it's going to look very similar to our previous second law of thermodynamics. Here we write it on a molar basis, and we have this we have to figure out how to do this term. What is that S bar? That's our entropy. But we need it to be on a consistent datum point for all measurements. And that introduces us to, believe it or not, there's a third law of thermodynamics, another law, and in it, basically, it's a statement about absolute entropy. And that's where we'll get to today, okay? So let's start with a problem. It's very similar to a problem that we solved last time. We have propane. It comes in at 25 C, 1 ATM, into a furnace operating in steady state, burns with 100% theoretical air. The air enters at a separate stream, 25 C, 1 ATM. So we have two inputs, the pure propane, C3H8, and the air into our combustion, and then the products go out, combustion products. Determine the heat transfer to the furnace, so that's this Q dot, in units of kilojoules per kilomole of fuel. So it's really Q dot over N dot of the fuel. When the combustion products exit at a given temperature, so the temperature exit is 1000 Kelvin. So how do we solve that problem? Well, we deploy our conservation of energy, and we have a sum, the stoichiometric coefficient. Then I'll just put the molar enthalpy. I know I need to use the enthalpy of formation and the deviation from standard 25C. But we sum over all the products that are exiting minus the sum stoichiometric coefficient, molar enthalpy, over all the incoming reactants. Look good? Well, we have to get a balanced reaction equation. So what is our balanced reaction equation? C3H8 plus so much O2 plus 3.76 N2 goes to how many carbon dioxide? 3. How many water vapor? This is an 8 right there. 4. So then we have 6 plus 4, that's 10. 10 divided by 2, 5 O2s are required. And so to finish it out, we have 5 times, I didn't leave enough room, 5 times 3.76 N2s. Is that our balanced reaction equation? Yep. Okay, let's press forward then. So what we're going to do is we're going to say, well, I need the stoichiometric coefficient, the enthalpy of formation on a molar basis, plus, this is going to be for each of the products. So I'm going to have it for CO2. I'm going to have it for stoichiometric coefficient, enthalpy formation, for the H2O, and stoichiometric coefficient, enthalpy formation of the N2. Now let me fill out some more of that. So for the CO2, it'll be the molar enthalpy of CO2 at the 1000, and I didn't leave enough room, did I? Minus the molar enthalpy at 298 for the CO2. So likewise, it'll be the molar enthalpy of 1000 Kelvin for the water, plus, I'll just make some more room over here, molar enthalpy at 298 for the H2O, and leave some room over here, plus molar enthalpy at 1000 Kelvin minus molar enthalpy at 298, close paren. This is for the nitrogen. So that's the sum over all the products. How about for the reactants? We'll have a minus the stoichiometric coefficient, the enthalpy of formation. I put the naught up there, forgot that. Plus the enthalpy, it comes in at 25 C or 298. And the reference is 298. And this is for, let's do the fuel first, C3H8 minus N enthalpy formation plus molar enthalpy 298 minus molar enthalpy. Why don't you just cancel some of these terms, Professor? Oh, I don't know. Oxygen minus okay, molar enthalpy of formation plus enthalpy 298 minus molar enthalpy 298, and this would be for the N2. And if I emphasize a lot of times, this is the N2 that's coming in with the reactants. This is the N2 going out with the products. All right, so which terms are zero? Yeah, the stable elements have a zero enthalpy of formation, so that's the nitrogen and oxygen, also the nitrogen in the products. All right, these cancel, right? Okay. And the fuel, that's right, for the propane. No difference there. And so we have to look those values up in our tables. And so we're going to be spending some time on the 1000 Kelvin temperature line to get it for the water vapor, carbon dioxide, and the nitrogen. Likewise, the 298. So we'll get this, need that value of H, that value of H bar, this value of H bar, that value of H bar, this value of H bar, that value of H bar, right? All right. So then you can stick them in, and when you stick them in and chase your units, you get a large negative number. Yes, sir.
So if the dew point temperature was, or if the temperature at the inlet was lower than the dew point temperature, would there be condensation at the inlet?
We have no water vapor in this air. This is dry right now, but yeah. You can calculate the dew point temperature. Typically it's 50, 60 degrees C-ish on the exit. And so if they're coming out 1000, you're pretty safe that it's in the vapor state for the water. But if it's coming out 298 Kelvin, well, no, it's going to have liquid. Yes? Yeah, this needs to be a subtraction right there. Thank you. Yep. Right? Very good. Thank you. So what I did was, here's a summary. It's put out a little cleaner. Maybe I should have just shown that. This is the balanced reaction equation. Where did we get the 18.8 from? 5 times 3.76. Very good. And then we have the very general sum over all the products minus sum over all the reactants. CO2, H2O, nitrogen, and the products. Then minus the sum over all of the reactants. And then you can see some of these terms are definitely going to cancel. And then when you stick in the numbers, you have 3 coming from the coefficient in front of the carbon dioxide. Enthalpy of formation, this is the value of carbon dioxide at 1,000 Kelvin and at 298. Look good? All right. All right, same problem, clicker question. So, same problem we just solved. Here's the clicker question. If the exit temperature of the product is 298 Kelvin, not 1,000, but it's now 298. That's the exit temperature of the products. Then the magnitude, forget about the negative sign. You know, it's just how large that number is for Q dot over N dot, right? We knew it was 1.4 million, okay? But what will it be? Will it be greater than 1.4 million? Will it stay the same, or will it be less? So hopefully you understand the question. All right, so we have a reactor, and we know that this is a Q dot going in, but I said the magnitude, so we know the direction is out. It's a combustion chamber. The heat transfers out of it, so it's just the magnitude. Now, what is 298 compared to 1,000? It was 1,000 Kelvin coming out. If it now is 298 coming out, isn't it colder? Isn't it colder coming out than what it used to be? So if somebody said, okay, if the exit temperature of the products is 1,000, which would be the right answer? It would be equal to. But now the question is, it's going out at a lower temperature, 298, so is it going to have a smaller amount or a greater amount? What happened here? Did I mistype that? Sorry, there's a typo. Right, but I think we understand. I was trying to compare the original value at 1,000. Okay? So do you want to redo this one, or you just want me to grade it? You want to do it again? 30 seconds. Oh, did you not get it in? All right, I'm going to ask another question. I'm going to do this. I'm going to have 2 parts to my combustion chamber. One is they're going to come in just like here, 298. No problem. 100% theoretical error, 298. And then it's going to come out 1,000. Right away, we know that that's the right direction. And you're going to get 1.4 times 10 to the 6 kilojoules for every kilomole of fuel going out. True? But it's 1,000 Kelvin. Now it's going to come out at 298 Kelvin. All right. In order for that to happen, am I going to have to put heat in? Answer A. A says I have to put heat in. Or take heat out of this second part. Answer B. Not that hard of a question. Down to 2 seconds. This always is frightening because I thank you for the 90%, but I still got 10% that are lost. All right, I don't know how to explain this. Hot gas make cold gas. I need to transfer stuff out. Cool it. I need to cool it. Do I need to cool it? All right. Now that we answered that question, this will be some additional blah, blah, blah. If I take both of these and add them together, is it going to be larger than this one or smaller than that one? If I, let's say I have $10, I give you $2. Am I going to have more than $10 or less than $10?
It's the same.
Oh, the same. Because I'm not going to really give you the $2, right? Okay, do you see what I'm trying to get at? Let's go back to my original question, this question right here, and ask it again. All right, now, what happened? I stopped that. All right. So, this was garbage. Yeah, this was the one I need to grade. I got 74% correct. Yeah. Now let's go to humble ourselves. That was the first attempt. Now tell me, I tried really hard to make this as understandable question. I'm surprised that only, hopefully the same 15%, and then added another, 10%, made it like 26%, like we're growing a little momentum. But then probably some of the first group said, I must be wrong, and changed. I hope not. Okay. Does this all make sense? Are you ready for a harder one? Yes or no? I'm going to cover up this one. And if the exit temperature is increased, let's say the exit temperature was 1,000, but now it goes out hotter, 1,500. That's an example of increasing the exit temperature. How will the magnitude, forget the negative sign, we know the direction, it's out of the system. How will the magnitude of Q over NF change? If the temperature goes up, then there's less transfer of heat out. So the magnitude of this will, true or false? Congratulations, 81%. Okay, you ready for another one? All right, this one's actually a little more challenging. You don't want that, do we? But hey, let's try it anyway. Cover it up. All right. If the percent theoretical error is increased, say it goes from 100% theoretical error to 150% theoretical error, what does that mean? We're bringing in more air than needed, more oxygen, more nitrogen than needed. How will the magnitude of Q, how will that heat of out of the combustion chamber, how will it change? Will it increase, remain unchanged, or decrease? I'm going to start it and give you a little time. There. Everybody in? All right. So let's do this. Let's go look at this equation. How does the equation change if I leave this 1,500, or leave it 1,000, but I have more air? If I put a 1.5 there, this goes up 1.5, and I have some oxygen left over. So how is that going to affect it? You're going to change the coefficients, aren't you? You're going to change the coefficient. Don't worry about the incoming reactants because they had 298, 298, 298. That part didn't change. This was 0 anyway. But the products going out, is this a larger number now? And do we also have maybe something with the oxygen in the products going out that also is added, another term. All right. If you increase the amount of air, how many people think they were right the first time or want to redo it? You were right the first time? How many people want to redo it? All right, redo it. There you go. 30 seconds only. Will the magnitude change? All right, we're in. Let's go ahead and look. Yeah, if you have more nitrogen and it's going out at 1,000 Kelvin, and there's some oxygen now going out at 1,000 Kelvin, then you're going to get less heat out because you only combusted the same amount. You only had the same amount of propane going in. So more sort of freeloading gases go out in the products hot, which is not what you want out of a furnace.
That's why it's good to burn pure oxygen.
For NASA, that's right. If you want the hottest products going out, you burn pure oxygen. Yep. All right, let's go back to this one. Well, okay, there you go. At least we did better. All right, now let's talk about adiabatic flame temperature. So you have an adiabatic combustor. So what's that mean? No heat transfer. In this equation, first of all, almost always we have no work. But if you have adiabatic, there's no heat transfer. So this has to equal 0. The sum over all the products must equal the sum over all the reactants. And so what happens is the enthalpy of formations aren't changing as a function of temperature. The inlet conditions are standardized, so it's always 298. You're bringing in 298 fuel. It's this term, you have the exit enthalpy as a function of temperature. If you put the adiabatic flame temperature there, 298, see that term right there? That will increase such that you finally get to the point where 0 is equal to 0. The right-hand side is equal to the left-hand side. All right? So if you take the same problem and you first of all let the products go out cold, you will get a large amount of heat transfer out of the gases, the combustion gases, out of that combustion chamber. It'll be like 2.0 times 10 to the 6 kilojoules per kilomole. You let them go out warmer, well, you get less, 1.4. If you let them go out 2,394 Kelvin, using all of the tools and calculations and techniques in the chapter, in the appendice for the data, or 21 degrees C, it'll be 0. Guess what is the adiabatic flame temperature for propane? That's the adiabatic flame temperature for propane. 21. We calculated it. Let's go and compare that number with out in the values that are in textbooks and other places. So you'll find that they quote the adiabatic flame temperature for a lot of common fuels, acetylene, butane, ethane. Here down here, natural gas, but here's propane. And you're burning it with air or oxygen. Notice your point you just made. If you have pure oxygen, the nitrogen isn't freeloading, and you'll get a higher exit temperature. That's the observation that you just made. But also, we just said in degrees C it was 21. Well, it's close to the reported 1980 degrees C, and it's off by some. But why are our predicted adiabatic flame temperatures higher than the experimental reported values out there? Few reasons. The real combustion is incomplete. Often it's you have excess air, slightly excess air. There are heat losses. When you see that blue flame, what are you seeing? Luminous. I mean, you could turn the lights out in the room. It'll still see the blue flame. It's not coming from lights reflecting off of a blue surface, and that's what you see. You're seeing the hot gases emit in the visible spectrum. And there can be some dissociation of the products, which will give a lower temperature of the exhaust. So this is our optimal estimate. But these are more measurements and reported values. Okay? Yes? That would be the next chapter. So if we have N2 and the presence of O2, you can disassociate to get two NOs. And that can be an equilibrium. And if you have a higher temperature, it favors pushing it that way. I got it? Yeah. In the reaction. All right. Well, let's move to entropy balance, or the second law of thermodynamics. Well, it's for steady state. Normally, we'd have the rate of change of entropy stored in the control volume with respect to time. But that's only if you're accumulating and depleting. Almost the whole class is steady state. Only a few true transient problems out there. And then we have this term. What is that? The transfer of entropy associated with heat. What is this B subscript on this temperature? Yeah, it's the boundary temperature. It has to be in Kelvin. We know that. And then what is this term? That's our transfer with the molar flow rates or mass flow rates. You could put it in terms of molar flow rates like it's shown here, or mass flow rates. But here, that's over all of the reactants coming in, products going out. And this last term, what is that? Generation due to irreversibilities. Do we expect that there will be irreversibilities? Sure. When you bring a fuel and just mix it with air, forget the combustion. You go out with just air-fuel mixed. Right away, you have some irreversibilities. But when you get to the combustion, even more. That's combustion's irreversible. And the numbers show that out. So this is our second law. The only challenge is the datum. Just like the challenge, how do we measure enthalpy when carbon rearranges itself? Comes out of the hydrocarbon, goes to CO2, and the hydrogen does the same thing. Well, they struggled with this datum point, and they come up with an absolute entropy. Now, we're going to deal with the ideal gases. There's only a limited set of data for the absolute entropy of, let's say, liquid octane at 25C, 1 atm. That value is in our textbook, but we really either are stuck with just a few values for some liquids and some solids at particular temperatures and pressure, as well as we can do a pretty good job of ideal gases. This is our equation for an ideal gas. Does it look familiar? Does it have a common structure that you're familiar with? Sure. This would be a function of temperature. This would be the function of pressure. For an ideal gas, the entropy is a function of both temperature and pressure. So this part, temperature only, and you can find it in the table. Let's go ahead and look for that in a table. So this table A23, we're introduced to the formula. We know the molar mass. We know the enthalpy of formation. We will not use the Gibbs function. I'm sorry, I've cheated you on your tuition. Skipped large sections of the thermodynamics textbook. 2 whole classes we couldn't even cover it all. Don't you feel cheated? How many times have you bought a thick book for a class and like 3 chapters? That's all it was ever covered. I was a student too. But yeah, I'm sorry, there's no way to cover Gibbs function of formation. But we are now covering this. We've already covered heating values, but now we're covering absolute entropy. So somebody's tabulated this. It's very hard to do, but they've done it. They've come in and they said, if you have pure carbon or hydrogen gas or oxygen gas or liquid water, this is the absolute entropy at 298, 1 atm. Okay? And so you pick that out. Also, if you go to, you can compare table A25 and table A23. For example, let's look at oxygen gas. Here's that 205.03 for the absolute entropy. If we come down and look at the temperature, same temperature, 298, and it's 1 atm, and we come over here for the oxygen, we have absolute entropy. These are same values. See that? So the data is consistent between the tables. You could take a look also. Let's take a look at water vapor. What's that, 188? Here's the water vapor, 188, same. All right, so let's back up a little bit. We know where to get this value from. Let's take a look at this part. What's R bar? Universal gas constant, right. What is Yi? Mole fraction of that species in the mixture, because you could have a mixture. What is Yi times P? Or maybe I should have asked what's P first. What's P? The pressure. Most times our gases go out in mixtures about 1 atm, but somebody could throw a loop, say, oh, it's 3 atmospheres pressure, or 5. But what is Y times P? The partial pressure. And so what you do is you normalize it to the reference pressure. Now, what do you think P ref is? Just take a guess. 1 atmosphere. Yeah. That's why in the header of that table they say 25 C or 298 Kelvin and 1 atmosphere pressure. Okay. So this is the partial pressure of that gas and the reference pressure. If it was pure gas, but maybe the pressure was 3 atm, well then you'd take the natural log of 3. But if it was a mixture, then you have the molar mass fraction, or not mass, molar fraction, Y sub I, the mole fraction, times the pressure. That's how you calculate it. Well, to get that absolute entropy, they basically have now what is called the third law of thermodynamics. It's basically, why do they use the term law in engineering and physics? It's like it can't be substantiated with anything before it. It's like it just has to be assumed and then work from there. Somebody shared with me where they said, and I didn't investigate it, that somebody has now proved from other things the zeroth law of thermodynamics. Hence, they're going to be able to strip the word law away from the zeroth law. It's no longer a law. That's how science and engineering change. But at some points, typically you just say, I don't know why, but this has always been observed this way. Energy is conserved, first law of thermodynamics. Similarly, the second law, here's the third law. So the third law talks about the absolute entropy of a pure crystalline substance is set to be 0 at absolute temperature of 0. So what do we know about a pure crystalline structure? What's the opposite of a pure crystalline structure? Would be an amorphous, just a mix. If you're a crystalline structure, you know, think about a molecule, you know exactly where your neighbors are. Oh, you're north, you're south, east, west, that direction around you. And if you're at absolute 0 Kelvin, thinking about a solid and a crystalline structure, do you think they are moving, vibrating at all? They are still. And so that's the reference point where for the absolute entropy is set to 0. Because think about it, on a molecular level, all the molecules are known exactly where they're at in relationship to all the other molecules. You start heating it up, things start vibrating and moving. And if you go to a liquid or amorphous solid or go to a gas, it even has higher values of entropy. Well, they had to do that. They had to put them all on the same consistent entropy measurement scale. Well, we have a few minutes. Let's solve this problem. We have carbon monoxide. It's a fuel. It can combust. It's coming in at 25 C, 1 atm, enters a furnace operating in steady state, and burns completely with 100% theoretical air entering in a separate stream. So we have two things, our carbon monoxide and our air. And there you go. And the first, it's a well insulated. So what is Q dot? 0. It's well insulated combustion chamber. First part A, what is the exit temperature? What temperature are they asking us to calculate? The adiabatic flame temperature, yeah. Okay. Then for part B, what is the rate of entropy generation within the reactor? All right. What are they going to be asking us to calculate there? Sigma dot divided by N dot of the fuel. All right. So how do I calculate the exit temperature? Get a balanced reaction equation for the carbon monoxide. Here's my O2 plus 3.76 N2. Okay, it produces carbon dioxide, CO2, one of them. How much water does it produce? H2O. I'm so used to burning a hydrocarbon that I want to put water in the products. But is there any hydrogen? No, there's no hydrogen in the fuel. No need for it. Okay, how about the N2? Sure, we're going to need that. We'll balance that out. So I come back and I balance the oxygen. Clicker question, do I put a half there, 1 there, or 2? Answer A, B, or C in order to balance the oxygen. Do I put a half? Answer A. Put a 1? Answer B. Or 2? Answer C. To balance the oxygen. All right. Well, what percent correct? So the oxygen balance, if they said B, which is common mistake, what did they forget to look at? The oxygen in the fuel. That's what they forgot to observe. The oxygen in the fuel. Did I encourage you to look for the oxygen in the fuel? Yeah, I did. So, yeah, give me that same problem on the test. Is that what you said? Maybe. But anyway, B is not correct. It's 1/2. All right, true? All right, now let's go forward. We do an energy balance. We've done that enough. Guess what the flame temperature comes in? Pretty hot, 2663. But let's do the sigma dot divided by n dot of the fuel. How do we do that? We're going to have the n times S bar for each of the products. So this will be for the CO2 and the NS bar for the nitrogen minus the NS bar for the CO minus the NS bar, I didn't leave enough room, O2 minus the NS bar for the nitrogen. This nitrogen is in the product, that nitrogen is the reactant. Okay, so I have for this stoichiometric coefficient, well, what does each one of these look like? They look like S bar naught as a function of temperature. So for the carbon dioxide, it's going out at 2663 Kelvin minus R bar, we know what that value is, the natural log of Y of the CO2 times the 1 atmosphere pressure, 1 atm, divided by 1 atm reference pressure. They cancel. It's just the natural log of the mole fraction of the CO2 in the products. All right. What's the mole fraction of the CO2 in the products? Is it, I forgot to put the half here, didn't I? Is it 1 divided by 1 plus 1/2, 3.76? Yes or no? Yes. You're right. That's what it is. So you can get the mole fraction. So that's how you get it. Now, same thing for the nitrogen. You'll have to get this values there. How about here for the carbon monoxide coming in? It's S naught bar of the carbon monoxide at 298 Kelvin coming in minus R bar natural log. Look at it, it's a pure stream of carbon monoxide at 1 atm. So what is the mole fraction in the pure stream? 1. And the pressure is 1/1, so the natural log of 1 is 0, and that term gets blown away. All right, you do the same thing for the oxygen and the nitrogen in the products. And you'll come up with 165. For the entropy generation within the reactor, it's 165 kilojoules per kilomole per, kilojoules per Kelvin kilomole of fuel.
How do you know that the pressure of the exit air is 1 atmosphere?
Well, if it doesn't say anything, there's nothing to increase the pressure. It's just a combustion chamber, so 1 atm. I guess you have to assume it. Any other comments or questions? Are you tired? We're done for today. Thank you very much. We'll see you.